All right, let's dive right in. We're going to talk about something that's literally all around us, all the time, but we rarely stop to think about it: the incredible physics of waves.
I mean, think about it. An ocean swell, a guitar string, a radio signal. What could they possibly have in common? They seem totally different, right? Well, it turns out they're all governed by the same beautiful physics. And the answer, of course, is waves.
Okay, so what exactly is a wave? Here's the single most important thing to remember. A wave is all about moving energy, not moving stuff. It's a disturbance that travels, but the medium it's traveling through, it pretty much stays put. The classic example is a ripple in a pond, right? The energy moves out, but the water itself just bobs up and down.
To really wrap our heads around this, let's make it super simple. We're going to look at a wave on a string. It's a perfect way to see these kind of abstract ideas in a really concrete way.
So every wave has to start somewhere, with some kind of energy input. Here, it's just a flick of the wrist. That little flick creates a disturbance, this single bump we call a pulse. And that pulse starts traveling down the string, which, by the way, is our medium, the stuff the wave travels through.
Now pay close attention to what's happening. The pulse, the energy, is clearly moving forward down the line. But look at any single piece of the string. It's not moving forward at all. It just goes up and then back down. This is that key idea again. Energy travels, matter doesn't.
But the journey isn't over. What happens when that pulse hits the end of the string? It doesn't just vanish into thin air. Nope, it hits that boundary and has to do something. And what it does, well, that all depends on how the string is tied off. Is it a fixed end or a free end?
And check this out. With a fixed end, the wave reflects back, but it flips upside down. It gets inverted. But with a free end, where it can slide, it reflects right side up. This might seem like a small detail, but this single principle of reflection is behind so much, from how an echo works to how we use sonar to map the entire ocean floor. Wild, right?
All right, so that was a single pulse. But what about a continuous wave, like you'd see on an oscilloscope? To really talk about these, we need to get some of the lingo down. Let's break down the anatomy of a wave.
This shape here, the classic sine wave, is going to be our guide. Using this, we can break down the 4 key terms you absolutely need to know. First up, amplitude. This one's easy. It's just the height of the wave, from the middle line up to the very peak. You can think of it as the wave's intensity or its power. A bigger amplitude means a more powerful wave, kind of like a tiny ripple versus a giant tsunami. Next, we've got wavelength. The name kind of gives it away, right? It's literally the length of one complete wave. The easiest way to measure it is from the peak of one wave, we call that a crest, to the peak of the next one. Okay, so if wavelength is about distance, our next term, period, is all about time. Imagine you're standing still and watching these waves go by. The period is just how much time it takes for one full wavelength to pass you. We're talking seconds here, not meters.
And last but not least, we have frequency. This is basically the flip side of the period. Instead of asking how long one wave takes, we're asking how many waves pass by in a single second. So a high frequency means tons of waves are zipping by really fast, one after another. Okay, so a wave on a string is great because we can see it, but what about something invisible, like sound? How does all this connect to what we're hearing right now? Let's make that jump from the visible to the invisible.
Well, it comes down to a really crucial difference in how the wiggling happens. That wave on a string was a transverse wave. The string moved up and down while the wave moved forward. That's perpendicular. But sound? Sound is a longitudinal wave. The vibration happens back and forth, parallel to the direction the wave is traveling. The best way to picture it is a slinky getting pushed and pulled. And this is exactly what a speaker does. As the cone moves forward, it squishes the air particles together, creating a little pocket of high pressure. We call that a compression. Then, as it moves back, it leaves a space with fewer particles, an area of low pressure, or a rarefaction. And it's this chain reaction of squishing and stretching the air that travels to your ear as sound.
And these pressure waves come at a huge range of frequencies. What's amazing is that we humans can only hear a tiny little slice of the full spectrum. Anything below our hearing range is called infrasound, and anything above it is ultrasound. There's this whole invisible world of sound going on around us.
And nature, of course, has figured out how to use this. You've got elephants using those super low infrasonic rumbles to talk to each other over huge distances. On the other end, you have bats using high-pitched ultrasound like a biological sonar to navigate and hunt in total darkness. It's the same exact physics, just applied in different, incredible ways.
Now for the really cool part. What happens when two waves run into each other in the same place at the same time? You might think they'd just crash and bounce off, but that's not what happens at all. They actually pass right through each other, and for that brief moment they occupy the same space, they combine. This is called the superposition principle, or interference.
So, if two waves meet and they're perfectly in sync, crest meets crest, trough meets trough, they add up. Their amplitudes combine, and for a moment you get one bigger, more powerful wave. We call this constructive interference. They're literally building each other up.
But what if they're perfectly out of sync? What if the crest of one wave meets the trough of another? Well, in that case, they can actually cancel each other out. You get a smaller wave, or if they're perfect opposites, you get nothing. Silence. This is destructive interference, and it's not just a weird physics trick. It's the exact principle behind how your noise-canceling headphones work. They create an anti-noise wave to kill the outside sound.
And finally, why does a shout sound loud up close but faint from far away? It's because the wave's energy has to spread out. Imagine a point source, like a tiny light bulb, sending out light in all directions. As the sphere of light gets bigger and bigger, the same amount of energy is stretched over a much larger surface area. So the intensity at any one point gets weaker, and it drops off really fast. That's the inverse square law in a nutshell.
So you see, waves are everywhere. They carry the sound of music to your ears, the light from distant stars to our eyes, and so much more. They're the fundamental way the universe moves energy around. So what other secrets of the cosmos are riding on these invisible ripples, just waiting for us to discover them?